Hello. In my last class I discussed on the structure of human eye and image formations in human eye, and in today's class I am going to discuss on brightness adaptation and discrimination. So brightness adaptation. So here in this particular topic we study how our human visual system can adapt to the changes in brightness and intensity levels, and how our visual system can discriminate these intensity levels. All that we will be studying under this particular topic. So we know that the digital images are displayed as a set of discrete intensity levels. The eye's ability to discriminate these intensity levels is of very important consideration in presenting the results of image processing. So the range of light intensity to which the human visual system can adapt is enormous. So that is in the order of 10 power 10. Starting from scotopic threshold to glare limit. So the range of light intensity levels to which the human visual system can adapt is enormous, that is in the order 10 power 10, starting from scotopic threshold to glare limit. That means this is the minimum and maximum limits in which the human visual system can discriminate the intensity levels. Okay. Now the experimental evidence indicates that the subjective brightness is the logarithmic function of the intensity of light incident on the eye. So the subjective brightness is a function of logarithmic intensity value of light which incidents on the human eye. So now here this is a plot of subjective brightness versus the intensity. Now what is this subjective brightness? Subjective brightness, it is nothing but the intensity level as perceived by the human eye. The actual intensity level is different and the intensity level as perceived by the human eye is different. That intensity level we call as subjective brightness, and this is the graph which represents the subjective brightness as a function of log of intensity. So now this solid curve represents the range of light intensity level to which the human visual system can adapt only in photopic vision, and this range is approximately in the order of 10 power 6. And the transition from scotopic to photopic is always gradual. So the transition from scotopic to photopic is always gradual, that is in the order from 0.001 to 0.1 millilambert, or it is from -3 to -1 millilambert in log scale. So we all know what is scotopic and photopic vision. Photopic vision is nothing but bright light vision and scotopic vision is nothing but dim light vision. So the transition from scotopic to photopic, that is dim light to bright light, is actually gradual, which takes place in human visual system, that is in this particular order. Now it is very difficult for a human visual system to adapt to this large variation in intensity simultaneously. Therefore, rather it accomplishes this by changing its overall sensitivity, and it is represented by this curve. So, this phenomenon we call as brightness adaptation. And for a set of given conditions, the current level of sensitivity is represented by brightness adaptation level, and it is represented as BA. And this range is restricted by the limit, that is BB. That means below this value it is indistinguishable black, which is visible to the human eye. So this is how a human visual system can adapt to the changes in the intensity level as well to changes in the brightness, and with the phenomenon of brightness adaptation. Okay. And this is all about brightness adaptation. So we learned how a visual system can adapt to the changes in the intensity levels with the help of this graph. Now let us study about the brightness discrimination. Let us understand this brightness discrimination with an example. Let me consider an opaque glass which covers the entire field of view. Let that opaque glass be like this, which covers the entire field of view. Okay. Whenever a light is incident from beyond this opaque glass, and this light is incident with the illumination eye on this opaque glass gives uniform illumination on this entire glass, and the intensity, this uniform intensity is represented by I. Now added to this, let me flash another short duration flash on this opaque glass exactly at the center of this opaque glass, that is here like this. This gives the added increment in the intensity value, that is represented by I plus delta I, where delta I is the added increment in the intensity when compared to the background intensity level, that is I. Now here, if this delta I is not bright enough, then the subject says no. That means there is no perceivable change. If this delta I is bright enough, then the subject says yes. That means there is a perceivable change. So now let me consider the ratio of delta IC by I, where delta IC is the incremental change in the intensity value compared to its background, that is I. So this ratio is the Weber ratio. This ratio is called as Weber ratio only when this delta IC value is discriminable 50% of times more than its background intensity, that is I. In such case, we call this ratio as Weber ratio. Now let us have a graph of Weber ratio as a function of its intensity. So now this is the graph. Where the log of delta IC by I versus log of I. Weber ratio as a function of intensity. Now this is the graph which represents Weber ratio as a function of intensity, that is log of delta IC by I as a function of log I. If the Weber ratio is large, then you can see that the brightness discrimination is poor. If the Weber ratio decreases, then you can see that the brightness discrimination is significant. So, these two curves represents the poor brightness discrimination and the significant brightness discrimination. And this significant brightness discrimination is due to the presence of cones in human eye, and this poor discrimination is due to the presence of rods. So, this is how the human visual system can discriminate the different intensity levels. So, in this topic we learnt brightness adaptation and brightness discrimination. Now, let me consider some examples to show the perceived intensity level of the human visual system. And this perceived intensity is always different from the actual intensity. So, to illustrate that, let me consider this figure. Now, look at this figure. This we call as Mach band effect. Here there are some series of strips. Each strip is having a constant intensity value. The actual intensity of each strip is represented by the horizontal line, okay? But when you look at these strips, you can observe that the left hand boundary of all strips are brighter and the right hand boundary is darker. So, observe these strips. So, the left hand boundary appears to be bright and the right hand boundary appears to be dark. This is because of the perceivance. This is because of the perceived intensity. So, this is the graph of the perceived intensity and this is the graph of the actual intensity. So, in this we can make out that the perceived intensity is different from the actual intensity. This is an example of the simultaneous contrast. So, now in this example you just observe that all the inner squares are having the constant intensity, but it appears that the inner squares intensity is progressively darker with the brighter background. So, this is an example of perceivance, and next is, so this is the figure which shows some well-known optical illusions. So, here look at this figure 1. In this figure 1, you can observe the outline of the square, though the square is not present in that picture. In figure 2, you can observe the outline of the circle exactly at the center, though there is no circle present at the center. And in figure 3, you can observe that the top line appears to be shorter compared to the bottom line, though these two lines are of same length. And in last figure you can observe that, and there each and every lines are parallel to each other, but it appears that they are far from being parallel. So, this is all due to optical illusions. So, the next topic is So, the next topic is image sensing and acquisition. So, here in this topic we will study how to acquire an image using sensors. Also, we will study what is a sensor, the structure of the sensor and different types of sensors, and how to acquire images using sensors. All that will be covered under this topic. A sensor is a device which produces electrical voltage as its output in proportion to the light intensity received by the sensor. So, usually the sensing devices what we use is a photodiode. Okay. So, there are three types of sensors. The first is single imaging sensor. So second is line sensor, and third is array sensor. So there are three types of sensor. So let me take up the first, that is the single imaging sensor. So here in this we use a single sensing element. Usually this is made of a photodiode. We know what is a photodiode. So this is a device which converts light energy into electrical voltage, and this voltage is in proportion to the light intensity received by the device. Right. So let us study the structure of this sensor. So now this is the structure of this sensor, single imaging sensor. Now this is the structure of the single imaging sensor. Now here, whenever the light energy is incident on this particular sensor, this sensor produces the output voltage. This voltage is in proportion to the intensity of the light received by this sensor. And this operation is done in combination with the power input and sensing material. Power input is required for the operation of this device, and the sensing material usually used here is the silicon material. Okay, and the filters are used on the front of this sensor. Here these filters are used for selectivity. That means this filter will select a particular band in color spectrum or a visible spectrum, and this sensor produces the output voltage in proportion to the intensity of the light received in that particular band. For example, if I use a green pass filter, then this filter will allow only the green band in the color spectrum, and this sensor will produce the output voltage in proportion to the intensity of the green light received by this sensor. This is how the filter works in a sensing device. So, and housing is nothing but this is like a case which encloses the sensing material. So this is all about the structure of the single imaging sensor. So now next is the line sensor. So now the line sensors are made up of series of single sensors arranged in a line like format, or they are arranged in the form of a strip. So this is how a line sensor looks. So this line sensor is made up of a series of single imaging sensor. They are placed in the form of a line or a strip to form a line sensor. Usually 4000 single imaging sensors are used to form a single strip. So these type of sensors are also called as sensor strip. And each individual block is also called as single sensor. Each individual block is a single sensor here. Okay, this is how the line sensor looks. So next is array sensor. So array sensors are made up of by placing these single imaging sensor in two-dimensional array format. So it is like this. And here each and every block represents the single sensor. So this is the array sensor. Usually this array sensor is made up of 4000 cross 4000 single array sensors. Okay. So this is all about the 3 different types of sensors and its arrangements. Next we will study how to acquire images using these sensors. So the first is image acquisition using single sensor. So just now we understood the structure and operation of the single sensor. So now here we will study or we will understand how to acquire images using single sensor. So here in order to obtain a 2-dimensional image, there should be a relative motion or relative displacements in 2 directions, that is in x and y direction. That is with respect to sensor and the image plane. So what I mean is that using a single sensor, if at all I have to generate a 2-dimensional image, then there should be a relative displacement in 2 directions, that is in x and y direction with respect to sensor and the imaging plane. So this can be explained better with an example. Now look at this figure. So this is a high resolution scanner. Now here the film negative is mounted on the rotating drum, and this rotating drum gives motion. This rotation gives movement in one direction, and the sensor is mounted to the lead screw, and this sensor can freely move on this lead screw. Whenever this sensor moves from left to right, this provides motion in another direction, hence providing motion in 2 directions to produce a 2-dimensional image. So whenever the sensor moves from left to right on a lead screw, it provides motion in x direction, and whenever the drum is incremented by 1 rotation, it provides imaging in y direction. So this is how the single imaging array is used to generate 2-dimensional image on a plane. So next is image acquisition using line sensor. Image acquisition using line sensor. Just now in our previous discussion we understood how to construct line sensors using single imaging sensors. So when these single imaging sensors are placed in series to form a line-like structure, this produces a sensor strip. So this is an example of a flat bed scanner. Here this line strip produces image, one line image in one direction, and the motion of this strip, the linear motion of this strip provides motion in another direction, hence covering the whole image, hence producing the 2-dimensional image on a plane. So this is how the line sensors will work, and these line sensors are usually used in airborne applications. So these line sensors are mounted to the aircraft which flies at a constant altitude and constant speed over a geographical area which we wish to image. So this is one application of that, and another application of this line sensor is in medical field. So usually that is in computerized axial tomography. So these line sensors are arranged in ring configuration, and the object which we wish to image is placed inside this ring configuration, and the X-rays are emitted from the X-ray sources which are concentric, and it can move freely on this ring configuration, and these X-rays are collected by the sensors which are at the opposite end, and these collected X-rays are used to obtain the image slices, cross-sectional image slices of 3D objects. This is how the line sensors are used in computerized axial tomography. The image of that is shown in this figure. Next is image acquisition using array sensor. So these array sensors are usually used in digital cameras, and they are also used in electromagnetic and ultraviolet sensors. And we know that to acquire images, basically images can be captured when a light energy is illuminated on the object which we wish to image, and this object emits a portion of the incident wave, and these reflected rays are collected by the imaging system, as you can see in this figure. And this imaging system in turn produces this on the 2D plane. If suppose this reflected energy is the light energy, then the imaging system uses lens, and this lens focuses this on the focal plane, and this focal plane is coincident with the array sensor, and each and every sensor which is present in the array produces electrical voltage, electrical output in proportion to the integral of the light energy received by that particular sensor. And the digital and analog circuitry present in this system sweeps out these electrical voltage and produces analog image. And the digitizer present in this system in turn converts this analog image into digital image. So this is how the array sensors are used to capture the images. So using array sensors we can acquire image in this fashion. Next is a simple image formation model. So how to form an image? We know what is a digital image. So what is an image? Image is defined as a two-dimensional function f of x comma y, where x and y are spatial coordinates. And the amplitude f at any pair of coordinates x comma y is the intensity level or the gray level of that image at that particular point. So f represents the amplitude or the intensity. So this is how the images are defined. So what is a digital image? When the values of x, y and f are all finite and discrete quantities, we say such images as digital images, right. So the function f of x comma y has a range from 0 to infinity, since the values of x, y and f are all finite and discrete quantities. So this is represented in this range. So I call this as equation number 1. And the function f of x comma y is comprised of two components. The first is I of x comma y, which is nothing but the illumination component, and R of x comma y is nothing but reflectance component. So what do you mean by illumination component? This is the amount of energy illuminated on the object which we wish to image, and reflectance component is the amount of energy radiated or emitted by the object which we wish to image. So the function f of x comma y is a combination of these two components, that is f of x comma y is the product of I of x comma y and R of x comma y. This I call as equation number 2. Now the illumination. So what is the source of illumination? Always the source of illumination is electromagnetic spectrum. So usually the range of this illumination varies from 0 to infinity, because for any electromagnetic spectrum the energy is finite and it is positive. So this illumination component ranges between 0 to infinity, and the reflectance is bounded by 0 to 1. That means there are only two possibilities with reflectance. Either the object should absorb the complete energy illuminated on that, which we call as total absorption, or the object should radiate the complete energy illuminated on that, which we call as total reflection. So here 0 represents total absorption and 1 represents total reception. So this I call as equation number 3 and this I call as equation number 4. So theoretically these are the ranges of illumination and reflectance, but practically the typical ranges differs. So the typical range practically for I of x comma y. So these are theoretical bounds. The practical bounds are, for example, if at all I consider the visible light. So during sunny day the visible light has the energy of 90,000 luminance per meter square during sunny day, and it is 10,000 luminance per meter square during cloudy day, and it is 1000 luminance per meter square in indoor, and it is 0.1 in full moon. So these are the typical ranges of illumination energy practically. So this is in sunny day, cloudy day, indoor and full moon. So similarly for reflectance, the practical bounds for the reflectance are, so this is equal to 0.01, the reflectance is 0.01 luminance per meter square for black velvet, and it is 0.65 for stainless steel, and it is 0.80 for white wall, and it is 0.90 for silver coat, and it is 0.93 for snow. So like this, the typical range of illumination and reflectance varies in practical bounds, whereas this we have considered on theoretical bounds. So now let us see how to find out the intensity of a monochrome image at a particular coordinate value x0 and y0. So the intensity level is denoted by L is equal to f of x0 and y0. So, for a monochrome image at a particular pair of coordinates, that is x0 and y0, its intensity level is denoted by L. Okay. So, now, and this intensity level, we know that on theoretical bounds, the digital images have the ranges limits from 0 to infinity, isn't it? But practically, for an image, it is the minimum intensity and the maximum intensity is which we represent. So, this is represented by, this is bounded by L minimum and L maximum practically for an image, and this is, so for a gray image, the minimum and maximum intensity levels are represented in this fashion, and usually this is equal to 0 and L minus 1. So, what is this L minimum? This is due to I minimum and R minimum, and this L max is due to I max and R max. So, this illumination and reflectance components gives the minimum and maximum intensity levels, and for a gray level it is represented by 0, L minus 1, where 0 is represented as black and this is represented as white in an image. So, this is all about a simple image formation model.